All right. And so that we want to have the framework for simulation by using the specific system. This a specific system we call MN1 queuing system. Why we have the specific one? Because we need to run simulation by given some distribution. First of all, M. M normally you think, oh, okay, it should be Markovian. If we have the property of Markovian property, actually it's exponential. Well, maybe you have a question. Exponential, we have an E, but why we want to use M? For some reason, some researchers propose a notation, and the proposed notation called Kane-Dow. All right, so Kane-Dow notation. Actually, we have 5 positions. At this moment, we just list 3. 3 of the 5 positions. We have M, M1. M actually is inter-arrival time. And here M again is the service time. And the third position is the number of servers. So M is a single server. So that's why we have exponential inter-arrival times, exponential service time, and then we have a single server. And so that we have a specific single server queuing system, MM1 here, for our simulation. Well, the notation, Kane-Dow notation is okay. Well, because of exponential, so we don't have exponential here. Even later in chapter 4, we will have the review of probability theory and statistics. For that part, I plan to have the free classroom. I recall the class for you and ask you to share because the background. So maybe you think you can read it, but I will have some advanced material as well. So for that one, let me think how to have the free classroom for that part. We have a simulation, and previously we already have the random number, this one, this random number, U. You think, oh, okay, random number, you can have the programming language with the library, that's true. But we want to alter based on the random number to have the other random number. So for example, we want to have exponential. So we have a formula for you. If we have a beta, beta means it's mean. All right, later we can mention it's mean. So mean inter-arrival time beta, and we follow the formula. Then this formula follows exponential. So it's exponential random variable. Well, maybe you have a question. Is it true? This one follows exponential? So we already have a checking. Why? About the checking, I already have 1 minute to go through. Go through first, and later I check it quickly for you. Take a look and think about, is it okay? So, anyone can let me know? it's proof. Why it's proof? 有没有人可以告诉我，哎，这东西在证明，那怎么个证明法？ So anyone can come up with some simple idea, the way to prove. Anyone? It's really no, or maybe yeah, some of you know this one, but you don't want to let me know. So first of all, we have a function. Cumulative distribution function. Cumulative distribution function says it's a function f of x. It's my cell phone. So let me check. So it's a function like this, so we always have this. And it should be associated with a random variable. And the random variable, we need to find the probability. For this random variable, to x. All right, so we follow this concept in chapter 4, we will mention this again. And to have this, so first of all, check it's a cumulative distribution function. So this one, the previous random variable, lower than or equal to s, so we rearrange it. And this is probability. And finally, uniform, we have for the two ends, so the probability should be this one minus this. So we have a probability here. All right, so if we follow the definition of cumulative distribution function, CDF, and then this one indeed follow the definition. And the first one, follow the definition. Yes, it follows the definition. But for the exponential, this is a given. Given probability density function. All right, so the given probability density function. Given probability density function, to find the probability like this, how to do? Actually, we perform integral. Integral from negative infinity to 0. 0 to the current 1. But why negative infinity to 0? Because 0 for that density, so it's 0, we drop that one. And so then we start from 0 to x. This is the given probability density function. If in shorthand, it's PDF. And in shorthand, this one, it's CDF. Sometimes we have a capital P, D, and F. So PDF. So this one, in fact, find the probability if we have the given density function of exponential, this form. You can look up exponential PDF, you follow the form. If you follow the form, then we have the result. Through integration, through integral, we have the result. And likewise, through the derivation, we have the result. Result 1 and result 2, they are equal. They are equal, so that says, oh, I don't know the distribution for this one, but I do know the distribution for this one. It's exponential. If you have a form like the CDF of exponential, of course, this one follows exponential. All right, so this is my way to explain why that formula follows exponential. Up to now, about the way to explain this one indeed follow the exponential distribution. If you know the reason, raise your hands. 到目前为止，我刚刚说你已经懂了，请举手。No? Okay, so let me re-explain this again. If I want to prove, we have the given exponential distribution. Follow this. All right. Right now, you can look up using your cell phone exponential random variable. Then you can find probability density function. It's this one. All right. And we are given a formula, this one. Oh, it's a random variable. The random variable can generate the exponential random variable. So CDF, like that definition, same like that definition, but we rearrange. Then we need to have the manipulation. We just try to rearrange it. Logarithm, so we remove logarithm, we will have the form using exponential. Using exponential, you should understand uniform. The upper value should be 1. So positive, but lower than 1. And then we have 2 bounded points. The 2 bounded values allow us to have the probability because of a uniform. Uniform, then we have 1 minus this. And this is a way to have the derivation. I think you can follow if you can review some of probability theory. But finally, this is the right result. And this one, you can perform integration through integral, then you can find the result. You can do it first. If you can do it first, and then we have the result. Here, just point out the result. Given exponential random variable should follow CDF like the form here. But a known distribution, maybe we think it's a known distribution, even we claim it's exponential, but we don't know it's exponential or not. But through derivation, derive the PDF. Oh, if you have a question, someone like, this is a CDF. Maybe it's another CDF, I have a tilde. It's another CDF, but finally we have the form. This form, the same as the form, so they are identical CDF. Identical CDF, of course, they follow the same distribution, exponential. All right, so I re-explain again. And this is the reason to have exponential for the formula. Okay, this formula can generate exponential random variables. Here, summarize its way to explain. Well, up to now, let me change my question to, if you don't understand, raise your hands. Yes, no, that's perfect, right?